4.3, we're looking at trigonometry extended, the circular functions. The first thing that we want to review is that an angle should be thought of as being formed dynamically by rotating a ray around its endpoint. And so what we don't want to assume is that, hey, if I just draw an angle, let's say a 30-degree angle, and we don't want to think of it as just a static object where one side was drawn and the other side was drawn and there it sits. As a quick little visual for you, what we want to be thinking of instead is that perhaps we've got, look at this circle here, and we're rotating around. And so we take that end point and it rotates around the circle to create our angle. And so as we look at the pictures that we draw today, you oftentimes are going to see a little arrow drawn as we put our angle there, because we want you to think, hey, we started with just one line on this side and we rotated it around the edge. So when we create our angle, some vocabulary that we want to be familiar with. The starting position of the ray is that initial side. The final position is your terminal side, and the amount that it's rotated gives you the angle measure. You are often going to see us start at 0 degrees right here, and that's our starting position, and we're going to rotate that angle around. Let's say that I rotate to right here. So here would be my terminal side, the ending point of that angle. Let's say this is about 135-degree angle here. So you had my initial side where I started, and then you had the terminal side over here. The counterclockwise rotation that you see has a positive angle measure. If I go to the other axis and I start again right here on the x-axis, but now I rotate in the other direction, let's say I'm going negative 45 degrees. Now if I'm rotating in a clockwise direction. So counterclockwise has a positive angle, clockwise has a negative angle. You notice that I started both of these at 0 degrees on that x-axis. That's known as an angle in standard position if that vertex is at the origin and the initial side is on the positive x-axis. We truly could start the angle anywhere within the 4 quadrants that we wanted to, but it's fairly typical to see it starting on that positive x-axis. Now, if that terminal side coincides with an axis, that's known as a quadrantal angle. So as we draw our angles in here, we've got a couple different options. So we know that we've got 0 degrees here, we've got 90, 180, and 270 in terms of our degree measurements. Just as a quick refresher, we could write all of those in radians as well. So 0 degrees is 0 radians. 90 would be equivalent to pi over 2. 180 is pi radians, and then 270 is 3 pi over 2. So when we're looking at what we're going to call a quadrantal angle, it's those angles that land on these axes. And so a 90-degree angle, if I was going to sketch that, would look just like this. We start with our standard position on the positive x-axis and draw that angle up to 90 degrees. So this would be a 90-degree angle that I'm going to graph. And then likewise, we could draw one at 180 degrees. Start on that positive x-axis. A 180-degree angle is really just going to look like a straight line for you. 270 degrees, start at that positive x-axis, but now I'm rotating. Here's 90, here's 180, here's 270 as I rotate around. So a 270-degree angle. I'm going to go down to that 270 degrees there. And then that would be our options. I guess I didn't draw a 0-degree angle, which would also be a quadrantal angle. And so that's starting at your x-axis and doesn't rotate at all, stays right there at 0 degrees. So those are our quadrantal angles. Next definition that we're going to see in this section, angles formed by different rotations that have the same initial and terminal sides are what are known as coterminal angles. And those coterminal angles, co for your prefix there, meaning at the same time, right? Co-workers, coterminal, 20 and 380 degrees. Let's sketch that. Here's a 20-degree angle, again, rotating from your positive x-axis. And what we're saying is, instead of just rotating 20 degrees, I'm going to go around one revolution, that's 360 degrees, plus 20 more. I end up in the same location. I've just gone one extra revolution around. So I went 20 degrees and then I went an entire extra revolution of 360 degrees to get me to that 380 degree angle. So 20 and 380 are coterminal with one another. Anytime we try to find any coterminal angles, if we're working in degrees, we're going to add or subtract your 360 degrees. If you were measuring in radians, you would add or subtract 2 pi, but it just means we're getting one additional revolution around that circle. So if we were asked to find 3 coterminal angles with 30 degrees in standard position, let's check those out. I'm going to draw just a quick picture of a 30-degree angle. And so if this is my 30-degree angle here, again, I'm rotating from my x-axis 30 degrees. So the coterminal angles, again, we could probably visualize just by rotating around this circle. So here was 30, but now I'm going to go one extra revolution around plus 30 more. That's going to get me to 390 degrees as a coterminal angle. Now, something else that we could do is instead of rotating around, now something else that we could do, instead of rotating around in this counterclockwise manner, we could rotate around clockwise. And so we know that 30 degrees was in the first quadrant there, but I could get to that same location, coterminal, by starting on the positive x-axis and rotating clockwise. If I do that, I haven't even gone one entire revolution. I've gone almost all the way around, just 30 degrees short of going all the way around that circle. So another coterminal angle would be negative 330 degrees. So it's 330 degrees in terms of the rotation. Because I'm going clockwise instead of counterclockwise, that's a negative angle. Now remember, we said you could add or subtract 360 degrees. So we recognize that 390 as 30 plus 360 degrees. We recognize negative 330 degrees as 30 minus 360 degrees. Now it says to find 3 of them. These are probably the 2 most obvious choices, add 360, subtract 360. You could continue in either direction to find the third coterminal angle. So you could either continue to add 360 degrees or continue to subtract 360 degrees. To come up with the third option, I'm going to add 360 degrees here, and that's going to get me up to 750 degrees as a third angle. And again, this one was done in degrees, but if you were working in radians, then you would just add or subtract 2 pi to the current angle. Another example that you might see in your homework, find an angle such that 0 degrees less than or equal to theta less than 360, and theta is coterminal with 512 degrees. So if I'm trying to find a coterminal angle, I know that all I need to do is add and subtract 360 degrees. However, this time it's giving me a range that I want to be in between. So in the previous example, I could decide if I wanted to continue to add or continue to subtract. In this case, our angle is already bigger than the angle that we started with. So we know that we're going to have to subtract. So we'll take that 512 in degrees, and we're going to subtract 360 degrees in this one, giving us 152 degrees for that coterminal angle of theta. Reference angles. This is going to be a pretty important definition for us, both in Chapter 4 and in Chapter 5 as we go through our trigonometry units here. The reference angle, it has to be positive. It has to be acute. So this is a positive angle. It has to be less than 90 degrees, and it's formed by the terminal side of theta and the x-axis. This is a big one over here. Sometimes people like to draw their reference angles to the y-axis. Always, always, always draw your angle to the x-axis to create that reference angle. Let's try it for one example. State the reference angles for 95 degrees. So the first thing that I'm going to do is I'm going to draw my original angle that they gave me. So I'm going to draw in a quick little x and y axis. And when I draw in my axis, I'm going to draw that 95 degrees. So we rotate again, starting from that positive x-axis just past 90. So here's our 95-degree angle. And then we're going to draw in that reference angle. So again, that reference angle says I'm drawing an acute angle. It's going to be a positive degree measure, and it's going to be formed by the terminal side of theta. So remember, my initial side was starting at your positive x-axis. Your terminal side is the end point where that angle ends, and that's the red line over here. So my reference angle is from the terminal side of my original angle, and I draw a line down to the x-axis. So always create your reference angle by drawing a line down to the x-axis. This little angle that I'm coloring in here in black, that is now your reference angle. I'm a little tight for space in there, so I'm going to write it off to the side. Usually your reference angle, you're going to refer to it as theta, and you'll see a little subscript as r to denote that it's the reference angle. Then the next thing we need to do is just figure out, well, how many degrees is that reference angle? We know that going off to the left here, this is 180 degrees. If I had rotated that red line all the way back down to the x-axis again, and so we are obviously shorter than 180, so we went 95. How many degrees from 95 to 180? Do some subtraction there, and that gets you an 85-degree angle for your reference angle. Now, before you move on to the other examples, what we want to point out is what's so special about this reference angle? What's it going to do for us? The angle that you were given was greater than 90 degrees. And we know how to use right triangles in a lot of different situations. But if we don't have a right triangle and we have an obtuse angle in there, then it's a little bit more complicated. And so what I want you to see on this slide, and this is not in your notes, but a comparison that I made on my calculator that I wanted you to look at. Our 95-degree angle, now obviously I had to double check that my mode was in degrees, and so always make sure that you're checking that throughout chapter 4 as we do our trigonometry, that you're making sure your mode is correct. If I type in the sine of 95 degrees, I get 0.996. The reference angle of 95 degrees was 85. So look down to the bottom for the sine of 85. Oh, look at that, 0.996. It turns out the ratio, right, the sine is our opposite over hypotenuse, and so that ratio, 0.996, is the same whether I use the actual angle or the reference angle. Now, the same is true for cosine and tangent. The only thing that's different that you're going to notice is that when I'm talking about a 95-degree angle, I've got a negative in front of those numbers. When I'm looking at the 85-degree angle, the reference angle, both values are positive. But aside from the negative, you see the same digits listed there for our value of our cosine and our tangent. And so it's either going to give us the exact ratio that we need or the opposite in sine, you see the negatives there, of the ratio that we need. And we're going to learn how we distinguish whether it's going to be positive or negative. But that's what the reference angle does for us. Helps us to do that calculation, allows us to use now a right triangle to do our computation and give us the decimal that we're looking for. So let's practice a couple more reference angles. If we've got a 218-degree angle, we're going to find that reference angle. Again, first thing I'm going to do is I'm going to sketch that angle out. So I'm going to rotate about 218 degrees. And then we say, okay, my reference angle is the angle from the terminal side up to the x-axis. So this is the triangle that we're looking at here. I'm going to fill in blue. That's my reference angle in there. And then once you draw the picture, it's pretty easy to tell how you're going to compute your reference angle. So sometimes people can do it without the picture, and if you can do that, that's fine. But making a sketch always is helpful to make sure that you are clear on what your computation is going to be. So in this one, when I look at it, I can tell that I'm going to take 218 minus the 180. That's going to give me a 38-degree reference angle for letter B. Letter C, 43 degrees. Again, quick sketch of a 43-degree angle in here. Rotating through to the 43 degrees. Drawing my reference angle, it says go from the terminal side down to the x-axis. Wait a second. Do you notice that when I drew that angle, that it's the same angle that I already drew, right? And go back to your definition. What were those main words? A reference angle had to be positive. It had to be acute. And we had to draw the line down to the x-axis. So this one is already positive. it's already acute. And when I draw the line, it goes back to the x-axis. So 43 degrees, you could look at it one of two ways. One way is it doesn't need a reference angle. The other way is that it's its own reference angle as you go through. In either case, we're going to say that reference angle is a 43-degree angle. Our last two examples are given to you in radians. Now, when you're given an angle in radians, you again have one of two choices. One choice, because we're more familiar with degrees, is to switch this into degrees first. And so we recognize this as 135 degrees. And so if I switch it into degrees, I can sketch my angle. I know 135 located halfway in between here. So that's my 135-degree angle. Again, a reference angle drawn from the terminal side down to the x-axis. And we do our subtraction here. We've got 180 line that we're basing things off of. So 180 minus 135 gives me that reference angle of 45 degrees. Now, another option, and something that I want to encourage you to start to do, is to think about this not in degrees, but to think about this still in radians, 3 pi over 4. You've been practicing with those angles, and we know that 3 pi over 4 is going to be here in our second quadrant. And we also know that we've got pi as 180 and pi over 2 right here as our 90-degree angle. And so as we draw in our reference angle, one thing that we can think of is, again, try to continue thinking of it in radians and don't switch into that middle of the road for our degrees as our reference angles. So we can look at this and say, hey, this was 3 pi over 4, 3/4 of pi. My reference angle needs to get me from 3/4 of pi down to 1 pi. How far is it from 3/4 to 1? That's going to be a pi over 4. So we can tell it by looking at the fractions in radians. You might have done it in degrees, and that's fine. And then once you get to your final answer, if they gave it to you in radians, your original angle, you just want to switch your final answer to radians in the end. So either way, you want pi over 4 as your reference angle. So it's just a matter of if you switch it to degrees first and then back to radians, or if you can think of it in radians throughout the entire problem. Letter E, state the reference angle for 5 pi over 3. Let's try to think about this one just in radians the whole time and not switch it to degrees. But you always have that option to switch it to degrees if you feel more comfortable with that. 5 pi over 3. One thing that I kind of like to do is to think of this 5/3 as 1 2/3 pi. So let's think about our quadrants and where 1 2/3 pi would be. I know that 0 is right here. This is pi over 2. Here's pi. That's 1 pi, right? And so 1 pi plus another 2/3 of pi. Here's 1 pi. Plus I need to go 2/3 of the way through quadrants 3 and 4. So if I went 1 2/3 pi, and remember back at 0 degrees is the same as 360 or 2 pi. If I went 1 2/3 and then I need to get to 2 pi, well, that might help us to think, well, what's our reference angle? From the terminal side up to the x-axis, my reference angle is this little chunk in here, right? And so what is that angle? 1 2/3 to 2. That's going to give me a reference angle of 1/3 of pi, or pi over 3. What's pi over 3 in degrees? That's 60 degrees. And so again, if you switch this to degrees to start out with, 5 pi over 3 is equal to 300 degrees. And so then you can look at that and say, oh, I can tell that that reference angle is going to be in 60 degrees, and then switch that back to radians as well. All right, next thing for us to look at in this section is the trig ratios in the coordinate plane. So we're going to have our angle theta be in standard position and a point P with the coordinates x, y be any point on the terminal side of theta. So our angle is from our standard position rotated through over here. So here's our angle theta, however many degrees that turns out to be. And then we're going to put a point P right on here, and that's the coordinate x, y. R is the distance from the origin to that point P. So this is our value R over here. And then we can draw this down to create a triangle. Now, if we draw that down to create a triangle, what does that tell us we know about R? If this was the point XY, it means we went over whatever that X value was. We went up whatever that Y value was. And then again, R is the distance of the terminal side. But that terminal side now turns out to be the hypotenuse of a triangle. And so if we wrote out the Pythagorean theorem, we would know that x squared plus y squared is equal to r squared. Or in other words, to fill in your blank here, if I solve for r, I would take the square root of each side. R is the square root of x squared plus y squared. So anytime they give us two sides of our triangle, we can find that hypotenuse, or the r value of what they're going to call that, by doing the Pythagorean theorem. Now, if we label these, similar to what we just saw on the previous page, as x, y, and r on our triangle, then we should be able to write out the trig ratios also based on that x, y, and r. Here would be my angle. In the case of what we had before, it would be our reference angle, but we know that those trig ratios are going to be the same. So if that's my angle theta, and we've got an x and a y and an r, check out my trig ratios. The sign is the opposite over the hypotenuse. That's y over r. The cosecant we know is the reciprocal of the sign, so that's going to be r over y, and I'm going to write that out at the same time. The cosine is adjacent over hypotenuse. That's x over r. And the secant, again, is the reciprocal of that, so I'm going to write that right away. That's r over x. And finally, we've got the tangent. Tangent opposite over adjacent, that's going to be y over x, and the cotangent, the reciprocal, that's x over y. These definitions are true all the time. So now, in addition to having the sign being opposite over hypotenuse, we can also always think of it as the y value divided by the r value. Now, with those values, and I reproduced them here in the upper right-hand corner, we can figure out the signs of the trig functions in all four quadrants. So I'm going to just label my quadrants here: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And in those quadrants, we're going to think about the values of x, y, and r. So let's start with the first quadrant and try to figure out what we know about those values. First off, in the first quadrant, the x value, x is always going to the right. Your x values would always be positive. Y is going up in your first quadrant. Y is also positive. And r, based on the Pythagorean theorem, and that being the hypotenuse of your triangle, we know that the r value is always going to be positive. So if x and y and r are positive, it would tell us that all 6 of these trig functions are also going to be positive. So I'm going to write all and then a plus there, all positive. Now let's figure out the same thing for x, y, and r in quadrant number 2. In quadrant number 2, I can see that to get to x, I'm going to have to go to the left. My x values are negative. In quadrant 2, to get to y, the y values are going up, so my y is positive. R is always positive. So if x is negative, y is positive, and r is positive, I want you to focus on the main 3, sine, cosine, and tangent. Which one of these 3 is going to be positive if y and r are positive and x is negative? The sine is going to be the trig function that's going to be positive based on the y and the r. And that means also the cosecant is going to be positive as well. In quadrant number 3, again with the x, the y, and the r, paying attention to what's happening for each of those values. In quadrant number 3, x is negative to the left, y is now going down, so the y is negative as well. R is going to be positive. And again, looking at your 3 quadrants, I want you to focus on which trig function is going to be positive. And so from these 3 functions, if x and y are both negative, the tangent is going to be positive because a negative divided by a negative is going to give me a positive there. So I know the tangent is positive, likewise the cotangent would also be positive. Now, if you had to make a guess for quadrant number 4, you're going to probably guess the cosine and the secant because those are the two functions that we haven't looked at yet, but let's take a look through just to verify that. So in quadrant number 4, the x is going to the right, that's positive, the y is going down, it's a negative value, and the r value always positive. So again, focusing on your 3 main trig functions, which functions are going to be positive when x and r are positive values. Sure enough, if both x and r are positive, your cosine is going to be positive as well. And likewise, your secant. So that should tell you the functions in which everything is positive. Now, a little shortened form that you will often see us write is, I like to draw a little grid and then just write S, T, and C. Those are going to be the main trig functions, the sine, the tangent, and the cosine. And so when you see the STC, you know that it's representing these 3 functions. But you also know if the sine is positive, the cosecant comes along with it. When the tangent is positive, the cotangent comes along with it. When the cosine is positive, the secant comes along with that. So you do want to memorize in which quadrants our trig functions are positive and negative. Back when I was in high school, they used to give us the acronym All Students Take Calculus. We live pretty near to St. Cloud, so around here we usually remember it like St. Cloud, STC. If you have had Mr. Anderson before, you've heard him say in Algebra 2, chillin' in the STC. So if whatever way helps you to remember that all of them are positive in quadrant 1, STC is what you're looking at for quadrant 2, 3, and 4. Now with that information, let's find the values of the sine, cosine, and tangent in a couple different scenarios. Example, letter A, 210-degree angle. First thing, of course, is I am going to draw that 210-degree angle. So I start at 0 degrees, I rotate through to get to my 210 degrees. And then I'm going to say, well, I don't know what to do with a 210-degree angle, but if I can make this into a nice right triangle, I can do some evaluating. So I'm going to draw a triangle from my terminal side up to the x-axis, and this little piece in here is my reference angle. Now, if that's my reference angle, the question is, how many degrees is that reference angle? To get from here to 210, how many from 210 to the 180? That's going to give me a 30-degree reference angle. Now, if this is a 30-degree reference angle, that makes this a nice 30, 60, 90 triangle. So they didn't give me any side lengths, but if that's the 30 degrees, I know I can label this as a 1, and then a square root of 3, and then a 2. Now I do want to note the directions. The square root of 3 went to the left, so I'm going to call that a negative square root of 3, and then I actually went down 1, so that's going to be a negative 1 as well. Now that I have that triangle labeled, I should be able to do some evaluating. What is the sine of 210 degrees? Notice that I'm not writing it with the reference angle. I'm not writing this as a sine of 30. They asked me about 210 degrees, so that's what I'm going to evaluate. But when I look at my picture, the sine opposite over hypotenuse, that's going to be a negative 1/2. The cosine of 210 degrees, adjacent over hypotenuse, that's going to be a negative square root of 3 over 2. And finally, the tangent of 210 degrees, opposite over adjacent, that's a negative 1 over a negative square root of 3. Those negatives would cancel out to both become positive. You can leave it as 1 over the square root of 3. You can rationalize if you like and multiply the top and the bottom by the square root of 3, giving you a final answer of square root of 3 over 3. Now, when you look at these, the one thing that I want to point out to you, since we just talked about the quadrants in which our trig functions are positive and negative, and I'm going to redraw it here real quick. You've got the STC happening here. And so we would expect that this 210-degree angle that's in quadrant number 3, the tangent should be positive. The other two values should be negative. So look at my answer. Sure enough, I got a negative sine value, a negative cosine value, and a positive value for the tangent. So it's a nice little way to double check that our signs are correct based on this diagram that we had just created. Another type of example, letter B, angle theta, whose terminal side passes through the point 2, -1. We don't need to find the angle. We just need to evaluate the sine, cosine, and tangent for this one. And so the first thing I'm going to do is I'm going to plot this point, 2, -1. So I'm going to go to the right 2, and I'm going to go down 1, and there's my point. And this is where the terminal side is. So that means I'm starting on this positive x-axis. I'm rotating through until I get to this terminal side that passes through the point 2, -1. Now, if I draw my reference angle in there, again, that line goes from the terminal side to the x-axis. So here's your reference angle in there. We don't know how many degrees it is, but we do know a couple things about our triangle. Since this is the coordinate 2, -1, it means I've gone to the right 2 and down 1. And so I know two sides of this triangle. I can find the hypotenuse by doing the Pythagorean theorem. So you've got positive 2 squared plus -1 squared equals, I'm going to put r squared since we've been calling that value r. And that gives me 4 plus 1, or in other words, 5 for r squared. And therefore your r value is the square root of 5. Now that you know all of those, we can go ahead and calculate the sine of theta, the cosine of theta, and the tangent of theta for this picture. So again, our reference angle right in here, I'm going to fill that in black. There's your reference angle. So the sine opposite over hypotenuse is -1 over the square root of 5. You can leave it like that. There's really no need to rationalize. If you want to rationalize and write it as -square root of 5 over 5, you are welcome to do that. Again, this is in quadrant number 4, so I know in quadrant 4 I'm expecting the cosine to be positive and the rest of them to be negative. So sure enough, the sine was negative. Cosine adjacent over hypotenuse, that gives me 2 over the square root of 5, or rationalize 2 square root of 5 over 5 positive, as we expected. And finally, the tangent, opposite over adjacent, that's going to be -1/2 for our final answer there. Letter C, the sine of theta is 3/7 and the tangent is less than 0. In this problem, the first thing they told me was that my sine value is positive. Well, that actually doesn't narrow it down for me, does it? Because I know in quadrant number 1, they're all positive. And then you had the STC happen in here. And so your sine is positive also in quadrant number 2. So this narrows it down for us, quadrant 1 or 2. But it doesn't tell us everything. So from there, we're going to use the tangent. It says the tangent is less than 0. In other words, the tangent is negative. In which two quadrants is the tangent negative? It looks like quadrant 2 and quadrant 4. So quadrant 2 and quadrant 4 are the spots where that tangent is going to be negative. So my overlap looks like it's happening in quadrant 2. So if I was going to sketch this triangle, I would be drawing my angle in quadrant number 2, where the sine is positive and the tangent is negative. And then if I draw a triangle in there, I know that I can label my side lengths as 3 and 7 because those lengths come from our reference angle having an opposite side of 3 and a hypotenuse of 7. And then we can do the Pythagorean theorem from there. And we're just going to call this side x. So you do your Pythagorean theorem, x squared plus 3 squared equals 7 squared. X squared plus 9 equals 49. So your x squared is 40. And x is the square root of 40. You can leave it as the square root of 40 if you want. We're not all about simplification in this section. We could also rewrite this as square root of 4 times 10, or in other words, 2 square root of 10. All of those are acceptable. Now, this is my value of x from the Pythagorean theorem, but I do want you to note that x went to the left, and therefore, when I plot this on my grid here, that's actually negative square root of 40 because I've gone to the left. Now, as you evaluate, they already told us the sine of this angle, so I really just need to find the cosine and the tangent, and we're going to list those below. So looking at the picture, if I'm evaluating the cosine, adjacent over hypotenuse, that's going to be negative square root of 40 over 7, and again, you can leave it like that, or you can use negative 2 square root of 10. Tangent, opposite over adjacent. Now you've got negative 3 over the square root of 40. And again, you can leave them like that. There's no need to simplify, but you can simplify if you choose.